Okay, in this lesson we are working on scientific generalizing from a sample, and the work that we're going to do here is going to um, be a bit more precise than our other lessons where we're just sort of drawing generalizations. In scientific generalizing, the process is quite a bit more precise, and I want to show you the features of that kind of sampling. And the reason why I want to do that is because it's commonly found in things like polls and these sorts of things. So we'll actually, um, uh, I'm sorry, it's when we do studies of vaccines, and when we do studies of various things, these are the things that we find. And so I want you to kind of know a little bit about how that works, because there are important features in this sort of thing. Now, if you've taken a statistics class, some of these concepts will be familiar to you already. Again, we're not going to go into the math involved here, but we do want to cover the concepts behind scientific generalizations. So when it comes to scientific generalizations, from our last lesson, we had a couple vocabulary words that we had, right? So we had sample or samples, population or target population, and we had attributes of interest, or what we call the features. Um, those are all things that are clearly specified with what we call a framing, a sampling frame. So the sampling frame consists of all of those things. And we talked about the steps that are taken to minimize bias in samples, and the fact that having a bigger sample is better than having a smaller sample. And so we know that what happens when we do a scientific generalization is that we take a sample, and we're talking about a population. We've got this attribute of interest, so we've got our sampling frame set up. We take certain steps to minimize bias or any sort of skewing in our samples, and then we turn around and we use calculations from statistical mathematics to arrive at our conclusion. Now, some of the basic concepts of scientific generalizing is, number one, true proportion. Now, to say that there's a true proportion means that the proportion of a population, remember that that's the group we're drawing our conclusion about, that actually has the attribute of interest. So the true proportion is the proportion that we're talking about in our conclusion, right? The sample proportion is different. That's the proportion in our sample that has our attribute of interest. So in the sample that we did, just to place this about poor and smart, or rich and stupid, our true portion on campus we don't have. There is a true portion, but I've never surveyed the campus as a whole about whether they would prefer to be rich and smart or poor and stupid. No, rich and stupid or poor and smart. I got to get that right. I have sampled our class, and so the sample portion is the percentage in our class that does that, and typically that sample for poor and smart is 60%. I don't know what the true portion is in our target population, because I have not had a chance to really sample in a way that I know is not skewed, so I can't know what that is. But there is a true portion out there, and the true portion is what I'm attempting to derive by having an unbiased sample. When I have an unbiased sample, I get a proportion, and I should know that that sample proportion and the true proportion are identical. Okay? The other thing to note here, the other basic concept in scientific generalizing, is called the random selection process. We all know about this, right? If we are going to try to ensure that every member or that our sample is unbiased, one of the things that we need to do is make sure that our sample is unbiased. And the way to make sure that our sample is unbiased is by randomizing the process for people being in our sample. So drawing from our target population randomly should create a better, a better sample, a more representative sample. Okay? All right, a few more concepts in scientific generalizing. Margin of error or error margin. Whenever we sample, there is a variation. If we do more than one sample, not every sample will come out exactly the same, and not every sample will give you the feature in the exact same proportion that it is in your target population. So, for example, if I had a big, I'll get to this. It's in my slides. So we'll get to margin of error. The next concept that we want to know about is confidence level. Confidence level is the degree of confidence that we can have that our sample is within the margin of error. In other words, if there's a margin of error is a range that our sample will typically fall in to approximate the percentage of the feature in the or the attribute of interest in the target population. Okay, that's our margin of error, right? If I'm sampling from my population, then my samples are not always going to be in the same proportion as they are in my population. They're going to vary. They'll vary. The range in which they'll vary is referred to as the error margin or the margin of error, right? That's the range that they'll, so, and then sometimes, however, I will get a sample that may fall outside my normal margin of error, outside the normal range of percentages that I get when I sample. So confidence level refers to how confident I am, or the likelihood, I should say, that my specific sample is within the margin of error, that is the acceptable range of results from sampling my population. Okay, I will promise that I will develop this a bit further and try to make it a bit clearer, because at this point I assume it's not super clear to you what's going on here or what these terms mean. The last one here is statistically significant. When I say that a result, or when in these studies we say that a finding is statistically significant, what that means is that the finding is outside the range of chance. When we sample, chance plays a role, and but if our finding is super, super big, well, that's not likely to chance. If it's a minor difference, then it's statistically not significant, because it could still be due to chance. So again, I'll help you place this. So here's my sample to help you place this, right? Let's imagine that I had a 55-gallon drum and it was full of marbles. And assume that the marbles are 50% orange and 50% white. So I've got two colors in there, just orange and white, okay? Those marbles are all sitting in a 55-gallon drum, and I have mixed the marbles up. We can't just like pour in all the white, then pour in all the orange, right? I mean, you've got to get them in there, and you've got to mix them up really good. You have to randomize what's in that drum, okay? Now assume that I reach in and I pull out a handful of marbles, okay? Now, when I say pretend this is a random sample, that is, pretend that I have just stirred the pot and done a lot of stuff with that, okay? Assume that I've done that. Now, what do you think is more likely? Do you think it's more likely that I'm going to get exactly 50% in my sample will be orange? Or do you think that approximately 50% of my sample will be orange? Well, the obvious answer is that approximately 50% of the sample will have orange markings. They're not going to be 50% exactly, most likely. I mean, it could happen, but most likely I'm going to get something approximating 50%, not actually 50%, right? Okay, good. So notice that my sample is going to approximate what's going on in that 55-gallon drum. What's going on in that 55-gallon drum? That's my target population. And I know as a fact that my target population is 50-50. I only know that now because we're using this as an illustration. Typically, the target population is what you're trying to find out about through your sample. But I'm teaching this backwards to show you that if we know that our target population is 50-50 and we draw samples from it, we know, it's intuitive to us that we're not going to get exactly 50-50. Odds are, right? Odds are we'll get something close to it, but we won't get exactly that, okay? Now let's assume that we do this 100 times. So there's a 55-gallon drum full of white marbles and orange marbles, and they've been randomized because they've been mixed up, and we're reaching in, we're grabbing a handful, and then we're counting the number of orange marbles. And then we're throwing those back in and mixing them up, and then we reach back in and we grab another handful. And then we get 10. And every time we're getting 10, right? And we just keep doing this. We do this 100 times. Here's the question. Is each random sample going to have the same percentage of orange marbles? No. It clearly won't, right? The answer is obviously no. One time I'll draw and I'll get 6 orange marbles. The next time I'll draw, I'll get 4 orange marbles. Maybe the next time I draw, I get 3 orange marbles. Then the time after that, I get 7 orange marbles. Then the time after that, I draw and I get 6, and the time after that, I get 5, and then the time after that, I get 6 again, and then the time after that, I get 4. Notice that my samples are going to vary. So one sample will approximate what's going on in the target population, and over a series of samples, I should expect variation as well, okay? Now, some samples that I have then are going to be closer to 50% and others are going to be further away. What's important to note here is that larger samples will tend to be closer to 50-50 than the smaller samples. Okay? I hope that makes sense, but if I pull out 2 marbles, I'm either going to get 100% orange, 0% orange, or 50% orange, right? And as I'm drawing out 2 marbles at a time, it'll be 100%, 50%, 100%, 0%, 0%, 0%, 100%, 50%. And that's quite a big range, right? But if I grab handfuls of 100, what are the odds that 100% of those 100 marbles I pulled out of that 55-gallon drum are going to be orange? Very, very, very slim. My samples are much more likely to be closer to 50-50, what's really going on in that 55-gallon drum, the population, than in a smaller sample. That's part of the reason why we think that larger samples are so much better, is that it will more closely approximate what's going on in that target population. Now, the variation that we get in our samples, remember I'm pulling out 100 and I'm pulling out 10 each time, and I do that 100 times. So 100 times I'm pulling out sets of 10. I'm going to get 6, 4, 7, 5, 3, 4, 4, 6, whatever. Those are the number of orange marbles I'm going to get. That range is what we call the error margin, okay? The error margin then expresses the range of random variation from sample to sample, all right? Now, if you look in your book on page 243, you'll see table 11.1, and I'd like you to, if you can, get to your book. If not, you'll be able to look at it later and see these things, but try to get to your book. Flip open a new page and get to the digital textbook, and it's on 343, but if they happen to change the page numbers at some point, which is entirely possible, it's table 11-1, and in there what you'll see is this table, and this table has 3 different columns, okay? And the columns, if you look at it, the columns indicate sample size, error margin, and then corresponding range. Now let's walk through that quickly. The sample size is just the number of, in our example, marbles that we're pulling out in each sample. So initially I said 10, right? Pulling out 10 marbles. So there's our sample size of 10. Below that, a sample size of 25, a sample size of 50, 100, 250, 500, 1,000, and 1,500. Okay? Now, in the next column, across the row, you'll see corresponding margins of error. Now remember, a margin of error is the range that we should expect our samples to fall in their deviation from, in their departure from, in their getting away from what is true of the actual population. So I know that in the marbles case, I know that it's 50-50 in that 55-gallon drum. And here's what else I know. If I pull out a handful of 10, then the number in my hand, whether that's 7, 6, 5, 4, 3, 2, whatever that is, will be or should be within 30% of what's going on in that drum of the target population. Okay? So my samples will be either 30% or better above or 30% or better below the actual number in there, the actual number in that drum. That means that my sample size of 10, if you look at the far right column and where it says corresponding range, the range is just the plus 30 minus 30. So if you have a minus 30 and plus 30, the difference between them is 60. That means that my sample has a range of 60%. Somewhere within 60% of that of what's true in the target population is where my sample should end. But notice that as I increase my sample size, let's say I go to 100, then my margin of error, the variation in the samples I get, will decrease. They will all be within 10 percentage points of the actual number going on, which gives me a range of 20, which means that I know that the real number is within 20 percentage points of whatever whatever percentage I get in my sample. Okay, that's how we read this table. So notice, for one, that the larger my random sample, the smaller my margin of error, the smaller the variation from sample to sample. Okay, and so the smaller the corresponding range. Now notice at the very top, right under where it says approximate error margins, they have something that says confidence level of 95% in all cases. The question here and now is, what does that mean? What does that refer to? Well, the 95% confidence level just means that if you take infinitely many samples, 95% of them are going to fall within that error margin. That means that if I take an infinite number of samples of 10, 95% of the time they're going to be within plus or minus 30 of the real number going on in my sample or my target population. Okay? Now the flip side of that is that 5% of the time my sample will fall outside of that range. So if I'm drawing a sample of 10, what are the odds that I will get let's say I know that my drum is 50-50 orange and white, and I'm drawing samples of 10. What are the odds that I will get a number of orange marbles that is either 10, 9, 8, 2, 1, or 0, 5% that one of those will come up. 95% of the time, I will get, actually it goes up to 8. Because it's plus or minus 30%, the actual number is 50% in the drum, in the 55-gallon drum. And since my error margin on a sample of 10 is plus or minus 30, from 50%, that goes 80% to 20%. So 95% of the time, my sample will yield a number between 2 and 8. That's what that means. That means that 5% of the time, I'll get a 0, 1, 9, or 10. Only 5% of the time. Okay? That's what our confidence level means. It's how confident can we be that our sample is within its margin of error. Well, 95% of the time that's going to be the case. Okay? When we do a sample of 10. Now, notice, excuse me, in a sample of 1,000, if in that 55-gallon drum, let's say there are 1,000,000 marbles, 500,000 orange and 500,000 white, and I've got 1,000,000 marbles in that 55-gallon drum. And let's say that we pull out a sample of 1,000. What's the margin of error? It's 3%. 3%. So if I pull out 1,000 marbles, I don't know what, off the top of my head, I don't know what 3% well, 3% of 1,000 is going to be 30 marbles, right? Is that right? Somebody tell me. Yeah, that's right. 30 marbles. So I'll be between 530 and 470 marbles. If I pull out 1,000, I'll be between those numbers 95% of the time. If I pull out 1,000 marbles, doesn't matter how big my target population is. Actually, doesn't matter that it's 1,000,000. All that matters is the size of my sample. So if I pull out 1,000 marbles, I'm going to be within 3% plus or minus of the real number going on. That means that my sample will 95% of the time be between, I got to get this right again, 30. So 530 and 470, because that's 50-50 of 1,000 would be 500, right? So for plus 30, that's actually, would that be plus 3 would be 30, and minus 3 would be 30. So if you plus 30 and minus 30, you get 530 and 470. Now notice, that's a very tight range. Now we're at 6% range. 95% of the time, I'm going to be within a 6% range of what's really going on in that target population. That's why larger samples are much, much better, okay? But that's how to understand those terms: confidence level, margin of error, yada, yada, yada. And I'll have more to say about that in a second. For now, let's turn our attention to, this is an actual poll taken from Real Clear Politics. Gallup reported, this is an approval poll based of President Obama's approval rating when he was in office, and I forget the year. This was February of 2013, and it tracks it from his date of inauguration back in February 2009. And this particular one ends in February of 13. Now, if you look at this graphic, what you're going to see is that President Obama's approval rating at this time was at 51%. So they're saying that 51% of the people in this country approve of the job that President Obama is doing, okay, at this time. Now notice in the reading below, I want you to, let's see if I can, notice here, oh, I didn't mean to do that. I'm trying to, Well, anyways, I'm trying to highlight the writing below and it's not working. Notice here, Gallup tracks daily the percentage of Americans who approve or disapprove of the job Barack Obama is doing as president. Daily results are based on telephone interviews with approximately 1,500 national adults. Now, 1,500, go into your book. What's our error margin for 1,500? It's plus or minus 2%. But now notice something. In theirs, they say margin of error is plus or minus 3%. Well, what's going on? I thought that a 1,500 person sample should yield a 2% margin of error. Ah, well, what's happened is that they have adjusted their degree of confidence. Their confidence level is now higher. Because they've opened up the range that their sample can be in, they are now increasing their confidence level. Now, they probably have increased their confidence level to something close to 97 or 99%. And when we increase our confidence level, what happens to our margin of error? Well, the margin of error becomes either larger or smaller. And what did we notice from the prior slide? When they increased their confidence level, their margin of error became larger. Now, to some of you, this is still going to be like, I have no clue what's going on in this relationship between margin of error and confidence level. So I have developed this fantastic, beautiful way of illustrating it to you, and I'm being sarcastic here, but I've got a visual that I hope is helpful for you to see this relationship, okay? Confidence level, let's imagine that you had a cannon and you needed to hit a target at, I don't know, let's say 500 meters away, okay? Now, margin of error refers to how big the target is that you need to hit. Everybody with me? So if I placed a 3x5 card out there, you've got a small margin of error to hit that with a cannonball, okay? If I tell you to hit the side of a barn, you have a slightly larger margin of error. There's a bigger range that you can land in to hit that. If I say hit the side of a mountain 500 meters away, then you got a pretty good margin of error there, right? Pretty wide target to shoot at, okay? Margin of error, just think of margin of error as expressing the target that you're shooting at. And think of confidence level as literally just how confident you are that you can hit that target, okay? Now notice something. If I increase the target, I should be more confident that I can hit it, correct? And if I want to be more confident that I'm going to hit the target, then I should increase the size of the target. If I go to a shooting range and I want to be sure that I hit the target, what do? I throw a bigger target out there, right? That's how I can be. Oh yeah, I can hit that. Yeah, I can hit the target. Here, look. Here's my 6 foot by 4 foot target. Yeah, I can hit that. And someone else comes along and says, no. Here's a 12-inch by 12-inch sheet of paper. Hit that. What happens to my confidence level? It shrinks. It should shrink. Okay? But now notice this relationship, right? The higher my confidence level, the bigger the target should be. Okay? So if in a poll, I want to be more confident in my results. If I want to be confident that what I find in my poll is within the margin of error, what should I do? Increase the margin of error. If in my shooting, I want to make sure that I hit the target, what should I do? If I want to be more confident that I can hit the target, I should increase the size of the target, right? So if we want more confidence, one of the things that we can do is increase the size of our target. And that's why they increase the size of the margin of error. That's why you have a larger margin of error in this poll relevant to President Obama, that it was a 1,500, but it was a 3% margin of error. Why would they do that? Because they want to be more confident that their findings are within the margin of error. Okay, so what do? We increase the target. We increase the margin of error. Okay, there's another way that we can increase our confidence level without increasing the margin of error. That is, if I have to shoot a cannon and hit a target, and I want to be more confident that I'll hit the target, but let's say that I can't increase the size of the target. Well, what else can happen? Well, you give me more samples. You give me more shots at the target. So if I have 10 shots at that target, I'll be much more confident that I can hit it than if I only have one, right? And you don't have to increase the size of the target. I take my son out to play basketball, and I say, okay, you got one shot to get this in the hoop. He's not going to be as confident as if I tell him, you got 10 shots to get this in the hoop. Increasing the margin of error would be like increasing the size of the hoop he's shooting at, right? You get more room in your shot to make it. But if you want to leave that the same, then just give them the ball 10 times. Okay? All right. So, quick review then. Margin of error expresses the limits of random variation from sample to sample. That is, that's the size of the target that you're aiming at in the analogy. But really what that is as I'm drawing from my 55-gallon drum, the margin of error expresses the variation in my samples because they're not all going to be the same. They're all going to be within a certain range, however, and that range we refer to as the error margin. Confidence level expresses the degree of confidence that we have that our samples are within that margin of error. Okay? It expresses the probability, is what that word should be, that samples of a given size have values within the margin of error. And unfortunately, our two guys are standing in front of that. They're inconsiderate, but I can tell you what's supposed to be there. Anyways, that's just a quick review of the difference between error margin and confidence level and their relationship. Okay? Now, what should we take away from this? Number one, a larger random sample gives you a smaller margin of error at any given confidence level. By a given confidence level, I mean as long as we keep our confidence level at 95, then the larger sample, smaller margin of error. If we start playing with our confidence level, then it changes everything. But you set your confidence level first, and then you say, okay, if I have this confidence level, then let's do a sample of this size, I have this margin of error. This size, I have this margin of error. This size, I have this margin of error. The larger the random sample, the higher our confidence level at a given margin of error. So this basically says that if I do a larger random sample, then if I keep my margin of error the same, let's say my margin of error is plus or minus 3, then if I have a larger sample, I can be more confident in it. And my confidence level can go up there as well. Okay? Now, some points about scientific generalizations. Number one, in a large population of widgets just a thing we make, there is a true proportion that are broken. So let's say we're in a business and we're making widgets and we need to do some quality control. We want to know if our widgets work well. Okay? Now, to know that, or if there are any defects in our widgets, we want a large sample, okay? In a large portion of in a large population of widgets, there's going to be a true portion that are broken. So I know when I manufacture them, there's a certain percentage that are going to have a defect or that are going to be broken, right? That we call the true proportion. But to get at the true proportion, we do a random sample of that population, and from a sample, obviously, and that will give us our sample proportion. So we'll know from our sample the proportion or the percentage or the amount of broken widgets we have, right? And then the sample proportion is going to vary randomly from sample to sample. Remember, we call this the margin of error. The next thing to remember is that the larger the random sample, the more likely it is that the sample proportion will be close to the true proportion. It's not typically going to be exactly that, but we know that the larger our sample is, we zero in more and more and more to that precise number. I mean, imagine that there were 1,000,000 marbles in there, and let's say my sample was 1,000,000 marbles. Well, then I'm pretty close to accurate. In fact, I'm dead accurate, right? But since samples don't measure the whole population, the closer we get to measuring the whole population, the better that is, the closer we know we are to the true proportion. Okay. At a 95% confidence level means that in 95 out of every 100 random samples, where the number is, for example, 500, the sample proportion will be within 4% of the true population. Look at your book here, right? On table 11.1, at 500, we're plus or minus 4. So if I sample 500, doesn't matter the size of the target population, if I sample 500 of whatever, I know that I'm going to be within 4 percentage points of the true population. Okay? All right. Now, if at a 95% confidence level, my sample is 1,000, then what happens to my margin of error? It goes down. Now it's at plus or minus 3 percentage points. So now I know that my sample proportion is within 3 percentage points plus or minus of the true proportion. Okay? Now what happens if I drop my confidence level? I stay at 1,000, but I drop my confidence level down to 90. If I shrink my confidence level, then what happens to my target? It gets smaller too. So at a 90% confidence level, this means that 90 out of every 100 samples of 1,000, the sample proportion is going to be within 2 percentage points. That is, in a less frequent, in fewer number of times that I'm sampling, I'll get closer. Okay? Everybody with me on that? So the higher confidence level requires a larger margin of error. Since I lowered my confidence level, I can have a lower margin of error. Okay? Now, public opinion polls involve scientific sampling. That's what I gave you when we were looking at President Obama's approval rating. How much can we take from them depends on two things then. Number one, how well does the sample represent the population? Do they have the same related variables in the same proportion? And number two, this is important, are the questions neutral? Sometimes when we do public opinion polls, we ask questions that are biased, that incline people to answer one way or the other. And so we push people to arbitrarily show one answer over another. The mathematical calculations are done by trained pollsters, are generally uncontroversial, but the controversy comes up with how well our sample is done and whether our questions to elicit a response are in fact neutral. Everyday generalizations, usually based on small and biased samples. That's just a truth of the matter. And in that, when you have a small and clearly biased sample, you should be very careful to reject margin of error and confidence level indicators that exceed the strength of the supporting evidence. Here's what I mean by that. In the English language, we express our margin of error and our confidence level. Okay? Well, let's keep going with the slides because it's the best way to explain it. Margin of error indicators. Remember that margin of error refers to that target. So think of the language that we use to describe how we'll do at hitting the target. I will hit exactly here. I will hit around here. I will hit about here. I will hit approximately here. I'm referring to my margin of error, right? If I say exactly, then I've got a pretty small margin of error. If I say around, I'm giving myself a lot more wiggle room, right? I'll get the ball exactly there versus I'll get the ball around there, okay? That means that I'm giving myself a large margin of error. Confidence level indicating words are things like possibly, maybe, probably, almost certainly. All of these words express how confident we are that we'll hit the target. Now, we use these in combination. It's possible that I'll hit around here, right? If I'm looking at the bullseye of a target and I say, it's certain that I'll hit exactly this spot, then I'm very confident and very precise, very small margin of error. But if I say something like, well, maybe I'll hit around here, then notice I'm not very confident and I'm leaving myself a pretty big range of where I'll hit. When we have small samples, we have to be careful that the language should not express a small margin of error. It should express a large margin of error because our sample is small, right? Notice in a sample of 10, what's our margin of error? It's pretty wide, so we don't want a very precise expression, word for our margin of error. We don't want to say exactly. We want to say approximately or around or could. I'm sorry, not could. That's actually confidence level. If I have a small sample, how confident should I be that it's within the error of margin of error? Not very. Because the odds are much better the smaller the sample that you will fall out of your margin of error, or that you could anyways. Possibly, maybe, probably, almost certainly, all of those again express the degree of confidence that we have. A couple more informal confidence level indicators. Possibly, quite possibly, probably, very probably, I'd bet the farm. I'd bet the farm is a very high level of confidence. Informal margin of error indicators, these all come from your book, by the way, exactly around, approximately, about, give or take. Where are you going to hit? Give or take, somewhere around there, in the ballpark of, okay? In real life generalizations, your confidence level depends on your margin of error. So a safe bet matches a high confidence level with a wide margin of error. That is, if you're really confident, give yourself a big target. If you've got a small target, back off your confidence level, okay? Don't bet the farm that a generalization holds unless you give yourself a wide margin of error. Don't have a high degree of confidence unless you have a high margin of error. All right, hopefully that illuminated some of what you read and worked through from scientific generalizing from a sample. All right.